We had introduced the concepts of image restoration in the last class, and we were discussing the various point splits function, and towards the end of the last class we had discussed the effects of motion blurring, where we had considered that in the x direction there is a uniform motion with some velocity v in the x direction, and we wanted to compute the point spread function for that. Now in that there is a small correction which has to be made. So before we go over to today's discussions, okay, let us do the corrections pertaining to the last lecture. Well, we had the function, that is the degraded image gxy, written as 1 upon alpha 0 integral 0 to alpha 0 u of x minus alpha y d alpha. This is exactly what we had got, where alpha 0 and alpha we had already defined. Okay, alpha 0 was by definition equal to v into capital T, where capital T was the time of exposure, and alpha by definition was equal to v into small t. Okay, so now what we did was that we had gone over to the 2 dimension, so that apart from integrating with respect to d alpha, we wanted to integrate with respect to d beta also. Okay, so that this same expression can now be written as gxy equals 1 upon alpha, and instead of trying to keep the limits of integration from 0 to alpha 0, we had converted both the integrations limits from minus infinity to plus infinity, and thereafter we had introduced the definition of the rectangular functions to write it as rectangular function with argument alpha by alpha 0 minus half delta beta, and this was multiplied by u x minus alpha y minus beta d alpha d beta. Alright, now in our last lecture this term u of x minus alpha y minus beta was omitted. Alright, so this term must be there because it is coming automatically, because it was u x minus alpha y, and we are making it into u x minus alpha y minus beta, and by introducing a term delta beta over here, then if the limits of integration with respect to beta is from minus infinity to plus infinity, only where we have beta equal to 0, okay, there we are getting a value equal to unity, and at all other places this is equal to 0, so that this function can be written like this. So if you look at this expression very clearly, you are seeing that the degraded image gxy is obtained by convolving the image, the original image u of xy, with the function, okay, which is given here, okay, the function which is being underlined. So this becomes the point spread function. This expression we got in the last class, but the point spread function has to be convolved with the original function. So please note that there should be a term containing u x minus alpha y minus beta in this expression for gxy. Okay, please note this correction. So now we will be going over to the next topic of discussion. Actually speaking, we had in the last class got the degradation model in the continuous domain, and the expression which we had got for the degradation model was, let me write it down once more. We had got this expression gxy equals double integral within limits minus infinity to plus infinity f of alpha beta h of x minus alpha y minus beta d alpha d beta. Alright, we had got this expression. Now this was under what assumptions? Can you remember the assumptions which we made in the last class for the function h. Correct? Not time, rather shift invariant and homogeneous linear function. So with the assumption of linear, shift invariant and homogeneous function, we were getting the degraded model in this form, that f of alpha beta is nothing but the original image function. F of xy rather is the original image function, and h of xy is being defined as the impulse response of the system, or rather the point spread function. Alright. Now this was in the continuous domain, but we have to work in the discrete domain. Okay. So we must find the equivalent expression for this one in the discrete domain. Now to do that, let us simplify our problem. Okay. Instead of considering a two-dimensional signal, let us begin with a one-dimensional signal. Okay. So we are attempting to make a discrete domain formulation of degradation model. So at first we attempt to do it with the one-dimensional signal, and then we can extend it very easily to the two-dimensional signals. Alright. So let us take an one-dimensional signal given as f of x. This is the original one-dimensional signal, and h of x is the impulse response for this one-dimensional system, right? And let us assume that x is a discrete variable, so that x is defined in the range of 0, 1, etc., up to some constant capital A minus 1 for fx. So that means to say we are taking capital A number of samples for f of x. Okay. And let us say that for h of x we are taking once again the samples of this h of x. Okay. And the number of samples for h of x need not be the same as the number of samples we are going to take for f of x, isn't it? They are going to be different. So let us say that we take capital B number of samples for h of x, so that for h of x, x is defined in the range of 0, 1 up to b minus 1, capital B minus 1. Alright. Now we would like to make a discrete domain formulation for the degradation model. So now if we want to convolve these two signals, obviously we have to do a convolution in the discrete domain. So if we want to do the convolution, okay, now since we have already taken the sampling functions, now we know that the sampling functions must be periodic with some period. Okay. And let us say that that period is equal to capital M, and we are going to have both f and x, f of x and h of x as a periodic function having capital M number of samples. Okay. So that there is no overlap in the period of fx and h of x. So what we are really going to do, we are going to choose capital M much higher than a and b. So if we choose M to be a quantity which is greater than or equal to a plus b minus 1, okay, if we choose M as a number of samples for both f and h, okay, having capital M number of samples, then it will be, then both f of x as well as h of x will be periodic with period equal to capital M. But the question is, we are having capital A number of samples for fx and capital B number of samples for h of x, and capital A and capital B are less than capital M. So what we do, we just extend the functions f of x and h of x by adding some zeros, okay, to make it a discrete function of length capital M. Alright. So let us add zeros, okay, to make an extended function. So let us call the extended function of fx as f suffix e x, where the extended function f e x is having capital M number of samples, okay, where capital A number of samples are the samples from fx directly, and the remaining samples M minus A, remaining number of samples, they are zeros. Alright. And very similarly, we consider the extended impulse function as, impulse response function as he of x. Okay. So if we take that, if we take it this way, then what is going to happen for the function g? How many samples are we going to have for the function g? Again, capital M, and that is going to be an extended function of g. So I can write the extended function of g, okay, as again g suffix e x, okay. This is to be written as what of fe and he? This is to be written as a discrete convolution, okay, as a discrete convolution. So what is the expression that we will be using? Fe, let us have a variable m over here, multiplied by he x minus m, okay. Is this enough? No, we have to do a convolution, but so that means to say, instead of integrating, which we were doing in the continuous domain, we must do the summation in the discrete domain. So this must be summed up for m is equal to 0 to capital M minus 1 in one dimension. Alright. Now this same equation, okay, we can write in the matrix form, in the matrix notation, matrix vector and matrix notation as G equals H F, okay, where we are taking how many samples of F? We are taking capital M number of samples, isn't it? So F is to be indicated by a simple vector, alright, and let us say, so Fe we should write, but rather, okay, we can write Fe0, Fe1, etc., up to the last element of this vector is going to be Fe m minus 1. Alright. So this is going to be the F vector, okay, that is to say the samples of the original image. And G stands for what? G stands for the degraded function, okay. Let us not call it as image because we are taking only one dimensional case, okay. So the G vector can now be written as GE0, GE1, etc., up to GE capital M minus 1. These are going to be the elements of the G vector. Alright. Now we can write, I mean, because since F and G both are of dimension capital M by 1, they are vectors, okay. What is going to be the dimension of capital H? H has to be an M by M matrix, okay. And going by this equation, simply considering this equation, Gex equal to this, okay. If we consider this equation, then how should I write the elements of this H matrix? Just think it over. H, capital H matrix can now be written in terms of the elements of HE, okay. So what will be the first row? Just think over. First row will be corresponding to GE0, that means to say corresponding to x is equal to 0, okay, and the elements, there will be capital M number of elements starting from small m equal to 0 to m minus 1. So can you tell me the first row elements? First row, first element HE0. HE0. First row, second element HE minus 1, because x is equal to 0 and small m is 1. so that it is HE minus 1 becomes the second element. So the second element is HE minus 1. 0 minus 1 means 1. I mean 0 minus 1 means minus 1.
This is a two-dimensional matrix, so there will be two coordinates, x and y.
No. 1 minute. This is a two-dimensional matrix, no doubt. Okay, but just see the argument of this is HE x minus m. We are considering only the x variable. We don't have a y variable over here. All right, we have only the x variable. The function is fx. One-dimensional function is fx, and its corresponding degraded function is g of x. So the extended function is fe of x. Extended degraded function is ge of x. So it is HE of x minus m. There is only one argument in terms of x. All right. So the elements of this H matrix will be, for the first row, HE minus 1. Okay. What is the next element? HE minus 2. And what is going to be the last element of this row? Minus capital M plus 1. HE minus capital M plus 1. Very good. 1 minute. We are coming to that. We will make use of the property of this H function, and we will get the matrix in a better form. I mean, right now I am forming the matrix directly by making use of this expression. I am not doing anything more. Okay, there is no other manipulation that I am doing. Only to get the first row, I have put x is equal to 0. Okay, and got the elements by varying m from 0 to capital M minus 1. Only that much I have done. Is that acceptable? Because I mean, I have already defined what this F matrix, F vector is, what this G vector is. Okay? Fine. Now, what is going to be the first, I mean, this was the first row. What is going to be the next row's first element? HE1. What is going to be the next element? What is going to be the next? The last? Minus m plus 2. Very good. What is going to be the last? I mean, like this, I can keep on computing. What is going to be the last row? Anybody? HEM minus 1. Next element? HEM. No, not M. M minus 2. Next element? HEM minus 3. So on. What is the last element? HE0. HE0 is going to be the last element, not one. I mean, we are considering here x is equal to m minus 1, capital M minus 1. Okay, so it is going to be HE0. Okay, because we are varying small m from 0 to capital M minus 1. All right. Now, again, since we are taking samples of this H function, okay, basically H functions also we have taken how many samples? Capital M number of samples. So naturally it is going to be periodic with a period equal to capital M. So we can straight away write the property that HE of x must be equal to HE of capital M plus x, isn't it? Always. So if we make use of that property, okay, then it is possible for me to represent all the elements of this capital H matrix. Okay, this arguments, okay, I can always write within the limit 0 to m minus 1. Okay, so if I write that, okay, just let us have this for reference. Okay, and let us reconstitute the elements of this matrix H. Okay, so the first element, of course, can be written as HE0 as it is. The next element was HE minus 1. What I can write for that? HEM minus 1. HEM minus 1. By making use of the periodic property here, HEM minus 2. And the last element? HE1. Very good. What is the next element? What is the next row? HE1, HE0, HE m minus 1, etc., etc., HE2. So on it goes. The last row, HE m minus 1, HE m minus 2, it remains as before, HE m minus 3, etc., etc., up to HE0. So this is the H matrix that we have got. Now, can you see some interesting feature of this H matrix? What do you observe? Rotating each row, rather by giving a circular shift to each row, we are getting the next row. So every row is a circular shift of the preceding. So what I do, simply if I give circular shifts to all these things, means if HE0 comes over here, HEm minus 1 goes one step, etc., etc., and lastly this HE1 comes back to this position by giving it a circular shift. What do I get? I get the second row. Again, if I give one more circular shift, I go over to the third row. And then if I give a circular shift to the last row, then I get the first row. Okay. So, do you know what this matrix is called? This is called as the circulant matrix. Very good. So, I have capital H. So, capital H is a circulant matrix. Alright. So, this is the composition of the circulant matrix for one-dimensional signals. Okay. And now we are going to consider, okay, what is going to be the composition of this H matrix when we consider two-dimensional signals. Okay. Of course, two-dimensional extension is quite simple. I think by now we are all familiar with the concepts of how to convert any two-dimensional array into a one-dimensional array by row ordering. That means to say, if we have an image of size m by n, okay, we can always make it into a vector of size mn, okay, and then proceed. Okay, so we will be making use of the same concepts, but let us have the very basic definitions of the two-dimensional functions. Okay, let us say that we have an image fxy, okay, which is of size capital A by capital B. We are assuming the image fxy to be of this size A by B, and we are also assuming that the impulse function, impulse response function h of xy is defined, is having a dimension equal to capital C by capital D. Alright. Now, we are going to extend this A by B and C by D images into an M by N image. Okay. So, M by N is going to be the size of the extended image. Okay. So, such that our definition of the extended functions I am now writing down. So, that means to say, in the extended function I will not call it as f of xy, I will call it as fe xy, and the extended h function I will call as he xy. Alright. So, the definitions of fe xy and he xy are: fe xy is equal to f of xy for x lying between 0 and a minus 1, okay, and what else? Y lying between 0 and b minus 1, okay, and this is equal to 0, okay, when x lies between a and m minus 1, or when y lies between b and n minus 1. Okay, and very similarly he of xy can be written as h of xy, okay, for x lying between 0 and capital C minus 1 and y lying between 0 and capital D minus 1, and it is 0 for x lying between capital C and M minus 1 or y lying between capital D and N minus 1. Okay, so these are the definitions of the extended function that I get. So I convert the function f of xy into an m by n image. I also construct an m by n two-dimensional function from the h of xy. Okay, so both I have converted to the image of size m by n. All right, and now with respect to the extended image, now this extended image, if I do a row ordering, okay, and convert it into a vector, what is the vector size that I will get? I will get vector of size mn by 1. All right, so in terms of these vectors, okay, I can write G equals, G is the degraded image, can be written as G equals HF, all right, where G and F are of dimension mn by 1. Okay, F is also of dimension mn by 1. And what is the size of H? H is of size mn by mn. Mn by mn. Of course, one thing we have omitted in this model. What is that? The noise term. Okay, and the noise, we were writing it as eta of xy in the continuous domain expression. Okay, so let us introduce the noise term also over here. Okay, and that we can write in terms of another vector again of size mn by 1. So to complete this equation, I can write it as hf plus n vector, where n is the noise vector again of size mn by 1. All right. Now, in the case of one dimension, we had seen that H was a circulant matrix. Okay. For the case of two dimension, okay, it of course remains circulant, but in terms of the H's which we had got for the one dimensional case, okay, we can represent the H for two dimension as a block of several such circulant matrices. Okay, and it becomes a block circulant matrix. Okay, so obviously capital H is of dimension mn by mn, and this we can regard as m square number of partitions. Okay, and each partition of size n by n. Okay, so we can write now this capital H in terms of block matrices, and the block matrix composition will be like this. The capital H matrix in two dimension is being written as H0 matrix, Hm minus 1 matrix, Hm minus 2, etc., etc., up to H of 1. The next row is H1, H0, Hm minus 1, etc., etc., H2. And the last row is H, M minus 1, H, M minus 2, H, M minus 3, etc., etc., up to H0. Okay, so it has become a block matrix, and again you see that the indices of this block the elements of this block matrix, they are again having a circular shift. So matrix H now is a block circulant matrix. Okay, and individually these elements H of these H matrices, okay, can be written as, if we take any indices, let us say H of J, if we take, then H of J will be a circulant matrix. It is a block of several such circulant matrices. So H of J, so in this expression we can write where H of J is a circulant matrix whose elements are HE J0, HE J1, etc. up to HE J1. Sorry, it is Jn minus 1, and it is HE J1, and then this is HE J1, HE J0, etc. up to HE J2, and the last row is HE J n minus 1, HE J n minus 2, etc. Last element is HE J0. Okay, and H of J is a circulant matrix. All right. So individually all these H of J's are circulant matrices. Okay, and all these circulant matrices, when I put into here, okay, the overall matrix H of size mn by mn now becomes a block circulant matrix.
In this case, if it is instead of n square elements, n square matrices, can it be n square matrix of size m square? Reverse.
What we have done is that we have assumed the image size as m by n. Okay, so that is why we wanted to put m rows, okay, in this matrix. Okay, I mean in this block matrices I wanted to put m rows, and that is why I have put it as H0, Hm minus 1, Hm minus 2, so that the x indices is changing from 0 to m minus 1. Okay, just to make it compatible with the image size, we did it that way. All right. Now, fine. I mean, what we did so far was nothing but the same expression for the convolution degradation. I mean, the same convolution expression for degradation we had considered, but instead of writing the convolution expression in the continuous domain, we are just writing the convolution expression in the discrete domain. And in discrete domain, we should remember this expression, that G, the degraded image, is equal to nothing but H of H multiplied by F plus N, where H is a block circulant matrix. Okay, so that is exactly what we have done so far, but so far we haven't done anything, okay, which should really help us in restoring the image, because after all, just remember always that what our problem is. Somebody has given us the degraded image G, okay, and we are going to make an estimate of F, okay. F also we don't know, okay. We are going to make an estimate of F, let us say that F hat, okay, such that F is very close to F hat, okay. But we haven't done that yet, okay. So in order to do that, we must thoroughly know the properties of this H function, okay, so that I mean some further mathematical knowledge about this H function helps us in designing the filter okay, which will restore the image. Rather, I want to get F from G, okay, and I must know the properties of this H very thoroughly. So now let us once again have a detailed look at the H matrix, okay. Let us go over to the H matrix definition, rather the circulant matrix definition for m number of points. We are considering once again the one-dimensional signal, okay. Take one-dimensional signal and I am having the definition of the circulant matrix like this: HE0, HEm-1, HEm-2 up to HE1, okay, and the last row is like this, all right. And now we define two new quantities, okay. The two new quantities which we are going to define is, one is that we are going to define a scalar function, okay, which I call lambda with some index k, okay. This I am going to define a scalar function which I will call as lambda k, and I am going to define a vector, okay, which I will call as wk, okay. This is going to be a vector, and I am going to define these two terms, okay, in terms of the elements of this H matrix. So my definition, if I define the scalar quantity lambda k as follows: I take these as HE0, okay, plus HEm-1, okay, into exponential to the power j 2 pi by m into k. So just see what I am doing. I have taken HE0 as it is, okay. When I am taking HEm-1, okay, I have multiplied it by a complex exponential term, exponential to the power j 2 pi by m into k. Means this is how I am going to define this lambda k, okay, the scalar quantity, plus I am going to write HEm-2, that is to say considering the next element HEm-2 multiplied by, I take the complex exponential j 2 pi by capital M into 2k, okay. Like this I form a series, okay, series consisting of how many elements? m number of elements, and the last element in this series is HE1, and what is going to be the multiplication factor for the last? Exponential to the power j 2 pi by m into m-1 into k. This is going to be the last term here. So that is how I define a scalar quantity lambda k. Lambda k is scalar, isn't it? You can clearly see lambda k is a scalar. And now the wk vector, okay, I am defining as follows, okay. The vector wk, so let me write down here that this is lambda k by definition. I have just formed a series, okay, and by definition I am putting that as lambda k, and wk vector, okay, is being written as, its elements are 1 exponential to the power j 2 pi by capital M into k, okay, exponential to the power j 2 pi by capital M into 2k, etc., etc., and the last element I am considering as exponential to the power j 2 pi by m into m-1 into k. So that means to say that in this expression, whatever complex exponential coefficients I had considered in this series, okay, all those complex exponential coefficients, if I consider and compose them into a vector, that is being defined as my wk vector. So the wk vector is defined this way. All right. So now tell me one thing, that if I now take lambda k into wk, okay, if I now take lambda k into this wk vector, okay, you can clearly see by making a matrix multiplication that this becomes equal to the product of my circulant matrix H and wk. H into wk, okay, is equal to lambda k into wk, okay, by matrix multiplication verify that HWK is equal to lambda k into WK. So what is the significance of this? Yes, so lambda k's are going to be the eigenvalues of which matrix? Of H matrix. And what are going to be WK's? WK's are going to be eigenvectors. So WK is an eigenvector of the circulant matrix H, okay, and lambda k is its corresponding eigenvalue. All right. So now see what we can do, okay. So we know that WKs become eigenvectors. And what is the significance of WKs? WKs, just see the elements of these WKs. The elements are nothing but the complex exponential expressions. Can you tell me the significance of lambda k, the physical significance of lambda k? Anybody? Isn't it very familiar equation? It is the, yes, speak out. Discrete Fourier transform of what? Discrete Fourier transform of the H functions. Discrete Fourier transform of the H function is clearly being written here, and that becomes the eigenvalue. The kth eigenvalue, okay, becomes the discrete Fourier transform, okay, of the HE function, the extended H function. All right, and this is something which we must remember, okay, because we will need these ideas, okay, later on. So we are getting the discrete Fourier transform, and that is the physical significance of these eigenvalues. So I have chosen the eigenvectors in such a manner that the eigenvectors are nothing but the complex exponential coefficients, and the eigenvalues are the discrete Fourier transform of H functions. Now WKs are nothing but the eigenvectors. Now using these eigenvectors I can form a matrix, okay, consisting of the columns of all these eigenvectors. How many such eigenvectors are going to be there? M number of eigenvectors are going to be there. So I can write W equals W0, the vector W0, the column vector W1, etc., etc. Lastly, the column vector W m minus 1. So all the columns I am just putting one after the other, okay, and I get a matrix W. All right. Now it is very now what is going to be the size of this matrix? W matrix? M by M. So it is a square matrix. All right. And it is very easy to show that W inverse, okay, can you predict what it is going to be? That is equal to W inverse W, and this is equal to the identity matrix R. So I is nothing but the M by M identity matrix. All right. Now, tell me one thing, that if I want to now get, if I want to diagonalize this matrix H, this block circular matrix H which I had got, okay, if I would like to diagonalize it, okay, what should I do? So I should write H equal to, this is by the property of the, I mean this is by elementary matrix property, I can write, because already I have got W as the eigenmatrix. W is the matrix consisting of the eigenvectors. So in terms of these W matrices, I can write H equal to W multiplied by the D matrix multiplied by W inverse. What is D? What is this D matrix? D matrix is the diagonal matrix whose elements are the eigenvalues of H. Okay. Rather, the same expression, if I pre-multiply by W inverse and post-multiply by W matrix, okay, then I can write down, then I get D. So from the above expression I can write D matrix as W inverse H W, okay, where D is a diagonal matrix whose elements are eigenvalues of H. Okay. And now we are going to extend this result. Okay, this result we got for one dimension, because I had considered H to be a matrix of size M by M. Now if I want to extend the result for two dimension, okay, then it is easy to see, okay, I mean you can proceed in a similar way, okay, and you can see that once again we have H equal to W D W inverse, okay, and D is equal to W inverse H W. So for 2D also we are getting a same result, but this time for the case of 2D, what is H? H is the block circular matrix of size M by Mn by Mn. So H is the block circular matrix of size Mn by Mn. And what is the physical significance of D's now? D is the diagonal matrix consisting of eigenvalues, okay, and what were the eigenvalues in the case of one dimension? Eigenvalues were the one dimensional discrete Fourier transforms, okay, of H function. And in the case of two dimension, the elements D, K, K, okay, the diagonal elements, if I write D of K, K, okay, these are the diagonal elements, D of K, K is become equal to the, they are the eigenvalues, or rather, they become the two-dimensional discrete Fourier transform of h function. Okay, so I can say that DKKs are related to the discrete Fourier transform of the extended function HE XY. All right. So now what we know? We know how to diagonalize the H matrix. Okay, because the property, I mean, as I was telling you, that the property of this H matrix is going to be very important for us, okay, in order to have a proper image restoration. Okay, and now we also know that how to diagonalize it. And one thing, remember very clearly, that in the process of diagonalization, what you are getting are the elements which do not remain in the spatial domain, but you are getting elements which are going to be in the frequency domain, the transform domain or the frequency domain. Okay, so whenever we think of restoring the image, okay, it is well possible that we will have to go over to the frequency domain, because all these W and W inverse terms are going to remain with us always, and multiplication by W inverse, okay, you can clearly know that multiplication by W will result in the transform domain, and then that result, if I multiply by W inverse, we are going to come back to the spatial domain once more. Okay, so naturally these are the things which we have to keep in mind in designing a proper image restoration. Okay, so we are going to discuss, we are going to utilize all the properties which we have studied regarding the discrete formalization of the degradation model. Okay, all the properties which we have studied, we will be making use of that in the next class. Okay, any questions? Thank you.